Good afternoon. So let's start with a review. We'll review a little bit about this hypothesis test. Okay. So when we get a sample, and we start with assuming our null hypothesis to be correct. So with that assumption, what does that mean? That means we will end up with a Gaussian distribution. All right. So this Gaussian distribution is supposed to be centered at population mean. Okay. With the standard deviation computed as your standard error. Then you will compute your sample mean, x bar, and by plugging this x bar into your distribution. So this point will be the z-score, which computed by using this formula. This is essentially to say I take x bar, I take away the population mean, and then divide by the standard error. So as I mentioned last time, the purpose to do this is try to normalize our Gaussian into a normal Gaussian, which is has 0 at the center with 1 as a standard deviation. So the purpose to this is we can reduce different Gaussian into this normal Gaussian, so we can easily calculate the CDF value. So because remember before, as I mentioned, during my study, we use a table. You will have a Gaussian distribution or normal Gaussian distribution table. So you can check at different z-score, what will be a corresponding CDF. But now, since you're using Python, you do not worry, but we still preserve this step. All right. So then by have this z value, we will know what will be the probability for everything smaller than this z value, right? So basically this area for this purple color. Right. So remember, since we have a symmetric, so we have two sides. So basically this two-sided test, the p-value will be the total area size of both sides. Remember that. By have this z value, then depends on your application, you may decide a significant level to say at what significant or at what how stringent you want to be to claim you want to accept or reject. So that is alpha is actually chosen by you. Okay. So from based on your application, if you think my alpha need to be this big. So when you choose the alpha, remember for this two-sided one, each side will contribute for this side will contribute half alpha. This side will contribute half alpha. Okay. When you decide the alpha, that means everything fall into this alpha area we call rejection area. We will try to reject our non-hypothesis. So basically, for example, in this example, when I draw, I have my purple area fall into my alpha rejection area. So in this case, we will say, if my p-value smaller than alpha, I will say, let's reject non-hypothesis. It doesn't seem this Gaussian distribution will be followed, right? So, but if your application allow you to pick a smaller alpha, you say, if my new alpha is to be put here. Say I only consider these two tiny region as my rejection region. So it looks like our z score corresponding to a p-value, which for outside of this rejection region. So we can't reject our non-hypothesis. We have to say probably this your non-hypothesis has to be accepted. Right. So this is a general procedure. Any questions so far about this procedure? We all know what this z-test try to do, right? Okay. It's actually a very simple idea, but if you do not really know what is this method doing, it can be very confusing. Yeah. So I mentioned how to compute the p values, usually because we convert everything. So doing this is what? You give me an arbitrary shape, any arbitrary shape of Gaussian. Sorry, my bad drawing, but I just say any Gaussian. If you do this, you will move your Gaussian into a 0 mean 1 standard deviation Gaussian, and with each point you will find one corresponding point here. So it's a kind of one-to-one map. So in this case, you can use the right mapped points to calculate your CDF by checking your table. And then you can, for example, I compute the CDF value for this Z as a purple. Then I can go back to my original, want to find the corresponding points by doing some algebraic. Basically, you can do the Z multiplied by Z SE plus U plus U. You will get back your corresponding X bar. See this process. We will see example of this. It's fine, right? Okay. So the reason, as I mentioned, the reason we want to get a normal distribution is because allow us to check some standard table. But in Python, we import a statistic package as follows, and then you can compute your z-score. Then you can calculate your CDF for that z-score. As I explained, since we have two regions, they are symmetric. So what we are trying to focus is to look at this negative z-score, because the CDF you calculate is just the CDF particular to this point. But if you want to calculate instead for this region, you have to calculate a 1 minus the CDF corresponding to this score, right? Because if I calculate CDF to this score, what I get is this whole region is everything to the left. So you have to do the 1 minus this. So it's doable, but just you have one more step. So we are lazy. So what we care is just we want to compute the CDF to this guy. So the value we can compute is already will be this half purple region. But the the p value contains 2 portions. So after you compute the area size of this, you have to multiply by 2. All right. Okay. So with this procedure reviewed, and we can ask ourselves what exactly the question we are asking here. Okay. So of course we define a non-hypothesis, we define alternative hypothesis, I mean, this non-hypothesis is always using H0, and alternative hypothesis we use H1, and then we manually define a statistical significant level alpha. Okay, this is alpha is really you choose, you decide based on your situation. And then we essentially we are ask one of the questions here. First, I think that this is where we stopped at the last class. So is a sample mean X bar in the tail defined by the alpha of the sample distribution? Because once you say alpha equal to, let's say 0.05, once you define alpha, you indicate the rejection area size, right? So basically then once you decide that, then you can check whether your X bar is fall into that rejection region or not. But in order to mathematically confirm that, you need to unify the alpha to make the alpha and your X bar comparable, because alpha is more is close to a CDF value, right? Is likelihood, but your X bar is a point on the horizontal axis. So you have to make them speak one language to another. A better way to say is try to get the CDF or the p-value corresponding to your X bar. And then you can see, you can compare the p-value with your alpha. One gentleman last time asked, how about if we compute the value corresponding to the alpha? Basically, you get this value. I mean, it's fine, but each time when you change the alpha, you need to recalculate, which is less convenient by adjusting different alpha. Okay. So this is the first question. Then there's another two equivalent way to ask this about the same thing. The second way is to say is a z-score in the tail defined by alpha. Okay. Because this essentially the difference here is when you ask X bar, you are talking about the distribution, sample distribution defined by the central limit theorem. All right. When you talk about the z-score, you are talking about a standard normal distribution. All right. So I think that I don't want to repeat because this is just a distribution conversion. By calculating your standard error, you are reduced your Gaussian from arbitrary Gaussian to a standard norm Gaussian distribution. Sorry. Correct. So the third way to ask the same question is say, is a p-value, which is calculated using this, less than alpha. This is what I try to refer as, you try to unify the language, make them to comparable. All right. I hope everybody get super clear about how this hypothesis test is trying to do. Any questions? So now let's see one. So actually we get back to our original example here. So recall our example, we have a factory as our supplier. The factory claim all our widget will follow specification to have a population mean of 100 and then standard deviation of 22. So then we get a batch of 100 samples. And we measure the average, the sample average to be 95. Then we want to ask ourselves, does this batch of widget follow the factory claim specification? So then to do this, we first define a non-hypothesis to say, okay, this is the specification is true. So this batch follows. Basically, this is a non-hypothesis. Basically, you say you don't need to do anything. Yeah, you just accept the claim. By defining the non-hypothesis, basically you will naturally have a sample distribution assumed. Okay. And then also you define your alternative hypothesis to say the specification does not be followed. So our goal here is to see if the non-hypothesis can be rejected or not. But again, it's critical to be aware, even we reject them or we can't reject the non-hypothesis, doesn't mean the non-hypothesis is true. Only say we do not have evidence to prove guilty. All right. So in order to check if the non-hypothesis can be accepted or can be rejected, but basically by try to plug in your sample distribution, sample mean into this Gaussian distribution to see whether it fall into the rejection region. In order to do that, the typical way is to first normalize our Gaussian to make it to be a zero mean, one standard deviation Gaussian. In order to do that, the way is very simple. Just try to compute a z-score by take away your population mean from your sample mean and divide by your standard error. This will naturally make your Gaussian to be a norm distribution, a standard normal distribution. All right. So now we compute the z-score, which is using 95 minus 100, then divide by this is a 22. This is a square root of your sample. I think that we all get this, and then you will get your z-score. This z-score is this guy, right? Because note, this is a standard normal distribution. And then we compute the z-score. This z-score corresponding to your, if you have your original Gaussian, which is has the mu, population mu as center, and then you have your sigma divided by this as your standard deviation. Then in this Gaussian, this is not the standard normal Gaussian. In this Gaussian, you have a X bar here at this place. Okay. But now I try to find the corresponding point of this X bar in my standard norm Gaussian, standard normal distribution, which corresponding to this score. Okay. And the area size to the left of this X bar is equivalent to this purple region. All right, because I repeat a couple of times of this same point, because if you do not have any background about statistics, I hope you get why we're doing this. Okay. So as I mentioned, this score is a point on this horizontal axis, but what we have is a alpha, is a rejection, significant level. That is the area. Okay, so in order to compare, you need to calculate what will be the size of this purple region. So to do that, we just try to first compute the CDF value of this Z point of basically this guy. Try to compute what is the size of this region. After compute that, this side is symmetric. So we use 2 times that. We will get a value, which is our p-value. Then you will try to make your conclusion at different significant level. By, for example, if I say I try to vary my alpha to be 0.1, 0.05, you can pick different, depends on your application scenario. All right. So in this example, if you say 0.1, which essentially we take half, right? So basically we are thinking, let's say put here, then this region will be 1/2 of the alpha. This region will be another 1/2 of the alpha, which essentially I'm talking this guy. So so this is a will be 0.05 for this area, right? Since our p-value will be equal to 0.02, and we consider also is a half of the p-value, or you consider total is that's fine. So basically our p-value will fall into this rejection region, and then we will say we can reject our non-hypothesis. All right. But if you pick up very small alpha, and we compare with our p-value, this is a, so basically you think you pick a very small alpha here. This is guy is greater than this. We can't reject because our either the z point or this x bar is fall outside our rejection region. All right. Are we okay with this example? So if no questions, I will move forward with an yes questions. If we have questions require you to do something, we will make sure you do not need to use any extra things. We will give you the information. You'll be giving us the all those CDF value, how to get those CDF value. If we really need you to have that, we will give you the information. And of course, one hint is try to usually one best way to remember is this 3 sigma rule. Yeah, because that is a 3 very commonly used CDF value. Right? 1 sigma away, 2 sigma away, 3 sigma away. Remember those values. Yeah. Okay, all fine. I try to be a little bit wordy about this topic because this topic is a very important topic. It's very simple, but I know for people who first time to touch with this Gaussian, we touch with those hypothesis, non-hypothesis rejection, can be a little bit confused. Yeah. But this is really a useful tool. You will find a lot of times people, probably this is a 1 or 2 mostly used by people who do not really do deep science. So even for outsider, they were talking about p-value. They are talking about test, right? Because you see that this example is a so typical example. Right? A lot of time you do need to make a conclusion to say whether this is a statistically significant or something. So it's a very useful tool. All right. We just talking about the one of the most common case. You have a point, then you have 2 sides. You want to see whether that point fall into those rejection region. But actually, there's a lot of other cases. For example, another very useful case is called 2-sample z-test. Think about that. If you have one population, you have another population, you ask yourself a question to say, does this 2 distribution has their mean statistically different? Right. So this is also another very popular scenario. Right? You can easily find applications. So basically, you have we take one sample, which has sample size n0 from one population, and then this is this from one population with a mean of mu0 and variance of sigma 0 square. And then we take another sample of sample size n1 from the population with mu mean as a mu1 and variance as a sigma 1 squared. So now you have, again, you have two samples. Instead of have one sample as before, but you have two samples. Now you want to assess whether they are mean to be different or not. Okay. Yes, questions? For for this one is still so when we talk about two-sided, usually we care about both smaller or larger. So we care about the different, whether the two things are similar or different, because large and small both are different. But if in the case, if we say we only care, does this larger than certain, then that will be one-sided. Okay. So in this case, we care about whether they come from, whether their mean are statistically similar or different. Still is a two-sided case. So now we are forming our hypothesis. It's actually very straightforward. So our non-hypothesis now is just to say, okay, their mean are the same. So basically, mu0 equal to mu1, and the alternative hypothesis, of course, is try to, because this is a fallback. If we reject our non-hypothesis, we will fall back to our alternative hypothesis. There, of course, we will say the opposite, to say their mean is not equal. So the difference now is to still think we eventually will have to use this central limit theorem, right? We will still need to form a Gaussian and think about there will be some kind of rejection region there. But how do we convert this problem into that scenario? Think about that. Yeah. So if I don't show you the next content, how would you do that? By using what we have learned so far. So first of all, you need to construct something corresponding to a Gaussian, right? So here, what we want to test is to, want to see their difference, right? So the things we are going to test now will be this guy. Will be the difference of these two means. Because if our non-hypothesis is true, then their difference need to be 0. Right. So now we start to have a Gaussian in mind. It have to be 0-centered. If they are similar, their difference have to be shaking around the 0, shaking around the center of my Gaussian. If the two mean are statistically different, then their difference have to be fall into the rejection region, to the tail of my Gaussian. Do you get that picture? Right? I hope this makes sense to you. But then there's still, we need to modify a little bit to calculate the standard error, because before we only have a one sample, X bar, you can easily calculate the standard error. But here we need to change a little bit. Sorry, there's empty space here. So now the standard error will be you compute using this way. Yeah, so still is very it's a kind of hope this I don't know how to explain this. So just remember for now, just remember this formula. Okay. Sorry, this is not corresponding to standard error yet. This is just the corresponding to the population variance, population standard deviation as before. Okay. All right. So now, essentially, this is what we want to compute. So during the actual test, during this actual two-sample z-test, we need to construct a difference between two sample mean, right? As I mentioned, you are hoping the difference is shaking around 0 without fall into the rejection region. Okay. And in order to compute, again, compute the so-called those p-values, we need to reduce our arbitrary Gaussian into a standard normal distribution by calculate the z-score. But the z-score now is you have the mu here, you have the mu here is 0. So basically this actually is you do not need to. Then you divide by the sample standard deviation, which is calculated using this. All right. So then everything else will be followed. Right. So this is a 2-sample test. It's very useful. You will see in reality, this is a lot of scenario may use this. When you compare two things, this methodology will follow. Right. Yes. It won't. Yeah, it won't, because you are surrounding 0, because you only care about fall into whether they are go far away into the tail or in the center. So you swap the order, swap the sign, they will be similar. Before they are going to the negative rejection tail, then now they will go to the positive rejection tail. Yeah. Yes, in the when we use one-side test, usually that scenario will be pretty clear. It's greater or smaller. Yeah. So are we fine with this? Because a lot of time when you try to compare two things, whether they are similar or different, you are able to construct some type of scenario like this. Yeah. So basically, you take samples from one population, you take another samples, and you want to see whether they have a similar mean or not. Then this will be a very easy way to follow. Yeah. All right. Are we fine with this 2-sample test? So the next topic will be the confidence interval. But before moving that, I want to make sure we are fine, because this is the topic we will cover till these slides for the exam 1. Okay. So yeah, feel free at this point to ask any questions about this topic. Otherwise, I will proceed to the confidence interval. And then on Monday, we will do maybe some question-based review. Yeah, you can ask questions about the material we covered so far, and then we can probably even have some discussion. And then we will not have lecture for Wednesday. Yes, that is your exam day. And then we will still have the lecture for Friday. Okay. So everybody know where the location and the time for the exam, right? So if you haven't checked the Piazza, go to check the Piazza post. We have the time, and also for people who have the DRC accommodation, I hope you already settled the actual location and the time. You're supposed to already know that. If you haven't, you can send me emails. I will. Yes, there's questions. What's the max number? Sorry? Let us do it if you have like, say 3 midterms on the same day. Oh yeah, I don't know. If you have time conflict, you can let me know. Yeah. No, it's not a time conflict. It's just that I have terminal and. Okay. Oh, okay. Yeah. I'm sorry to hear that. Okay. But if you guys do think it will make you feel much better to reschedule your exam, there's one possibility, but I can't promise. I'll accommodate that because there's a possibility I can fit you into the DRC section, which because this is will be taken at another time. Yeah. But because the location we reserved for DRC is not big, so I can't say. Yeah, you can try to log to send me emails, see if I can accommodate you. Yeah, try to talk to some professors. Sometimes they might have alternative dates. Yeah. But usually you need to give really good excuse or very good reasons. Yes, on Wednesday we will have the actual exam, but then on Thursday we may have some the DRC sections. So, okay. Great. Guess so. Probably I will proceed with the confidence interval. And this confidence interval is another super popular or super useful concept. I'm sure if you read articles, you probably will see things like this. Probably you never ask yourself, what does this mean? You will see a bar and with marked with something like this, right? I'm sure everybody see this before, but then what does that mean? So the reason I want to jump into the confidence interval is because I think that this is a topic best covered right after your hypothesis test. It's almost it's not precise but it's very easy to understand. But I think this is the other way, because in the hypothesis test we have a Gaussian, and then we have a population mean, and then we want to test. We are moving our sample mean to say whether it's fall into the rejection region or fall into the something around your population. But now the confidence interval is a little bit the other way to think. If I give you a sample mean, okay, I want to ask you where is the boundary to put your the population mean, which is give you some kind of confidence. All right. So in other ways, if I get this sample mean, so let me come to this. So let's first try to describe some of the definition. Then I will try to help you to, because this is a little bit not easy concept to answer about the confidence interval. Okay. So a confidence interval is a range around the mean, which says that how good is your estimation procedure. For example, if I want to claim a 95% of confidence interval, that may indicate a couple of things. Okay. So if I repeat the experiment a large number of times, 90% of the confidence interval would contain the population mean. So try to think about it. What does that mean? Yeah. Or before I run the experiment, there's a 95% of chance that population mean will fall within the computed interval. Try to pick one explanation which makes sense to you. They are more or less very similar. Yeah, very similar to. If the population mean is inside the confidence interval, it will not statistically significant. So informally, you will not be surprised. So among these three, they are more or less talking about something very similar. You can, at your preference, you can pick one to try to understand what do we mean here. So essentially, think about that. If this is your sample mean, you do one experiment. Okay, this is your sample mean. You are hoping you are hoping your, let me draw two things. Okay, you are hoping your the population mean will be not too far away from your sample. So of course, your population mean now can be either to your left or to your right. But you hope, no matter how you are different from your population mean, you're not too far away. When we're talking about, let's say 95, that essentially means this region will be 95. But of course, I draw because now you have a boundary, right? Interval, because this is your sample mean. You are go up or go below. You go up or you go below. The actual population mean need to be around you. Okay, and you will be sitting in a place. The area between your two population mean will need not be too big, because if you move too far away into, think about the rejection region. Of course, the rejection region doesn't apply here, but think about that. If you are stay in the tail region, that means you are kind of it's not going to be a good estimation, right? Because you already go too far away. Think about that. So this is essentially the things that this region between this guy and this guy, this region is we call confidence interval. So once you compute you have your X bar, you can compute something around your X bar to define how much value I can take larger, how much I can take smaller. I will consider that region to be my confidence interval because I'm more confident the actual population mean will be somewhere inside here. Why we can claim that? Because I know by the central limit theorem, my current estimation is not too far away from the true population. It's a little bit confusing, but I hope you get the main idea here, because we will go to see the actual calculation. But I hope you get the big picture. This is an interval. In the at center is my population mean. I allow to go a little bit larger, go a little bit smaller, but I want to make sure if I define this region, the true population mean have to be somewhere in between with, let's say, 95 confidence level. In order to do that, you have to make sure the interval is calculated in such a way. The region to the left, this guy is a X bar. Okay, this is your actual estimation, your actual sample mean. All right. So you want the region to your left and region to your right. Each shall take a half of the, let's say, 95%. This in total will be 95%. Or if you like, of course, you can go to, but this is not the right way, but you can think about a symmetric way to say this is 95. Yeah, but this is does not give you a interval. So you have to think about, let me show you a more better picture. Yep, something like this. This is your X bar. This will be your lower bound. This is your upper bound. So when you have this, then you repeat doing the experiment. Most of the sample mean will fall into your confidence interval. Okay, I hope you get a brief picture to say why we need this confidence interval. Then we will move to the actual, how do we compute the confidence interval? Okay. Let me see, do I have a better picture to show? Okay, this is probably the best picture. Okay. So this is your X bar. And think about if this is actually one extreme case to say, if I have a Gaussian, have this as my population mean, which here we do not know. And then if my X bar to the, let's say to the left, to the right of my mu will contribute to, let's say, half of my confidence interval, confidence level, sorry. Right, because if this guy move a little further, then I probably will have a Gaussian like this. Then this will probably fall into, before we call rejection region, right? It's going to be too unlikely. You see that? Because we are moving this guy. This blue thing is what we want to compute. It's not fixed. This red guy is what we actually have. We get a sample. We compute the sample mean, but from that sample mean, we want to see how far I can move left or right to create a confidence interval, right? So this blue guy, you think if I move this blue line further, then my red line becomes less and less likely, right? You see that, right? So this forming at a certain extreme case, this will become my boundary. So I'll have to stop here. If I move this red line, so move this blue line further to the left, this guy will become less possible. Similar for this guy, it's a symmetric. So this will create a lower and upper boundary of a confidence interval. Okay, so I hope you carry this big image, and next class we will see the actual procedure. Then after that complete, will not take too long time. After that, we will doing some question-based the review. Yeah, so see you next month.